Hi, this is Curtis Brown from Texas Instruments, and I'm here with Dr. Jones, my good friend.
Hello.
We're excited to do another smart space video for you. We're going to be talking about proportional relationships and linear relationships in this particular session. And in fact, I'm going to share my screen to go ahead and get us started. So I'm going to do that. Give me just a second to share my screen. So let's check this out. All right, so remember Dr. Jones, last time we were talking, we actually looked at this picture and this set of equivalent ratios, and we were kind of clicking through and seeing how ratios describe how one thing relates to another and how two vary together, all right?
Yes.
There's kind of this constant of proportionality, and they relate together somehow. Well, I was playing with that a little bit earlier, and I thought, well, what if we could take these same relationships, these same ratios, and we could put them on a graph?
Oh, that's great.
We graphed all of these things. This is kind of a cool setup. And in fact, I actually learned something when we were exploring this that I had never really thought of before. You know how when you plot equivalent fractions on a number line, they always line up on the exact same spot on the number line, right? When I plot, say, 1/2 and 2/4 and 3/6, it's always in the same location on the number line, right?
Yeah.
Guess what? If I take equivalent ratios, check out what happens. So I had the two blue circles to 3 green squares, and I'll put in 4 to 6, and I'll put in, say, 6 to 9, and I'll put in 8 and maybe 12, 10, something like that. Okay.
Yeah.
Look at what's happening with those dots. What do you notice?
Oh, that's so cool. They're kind of forming a line.
They're forming a line. They're going exactly up in a linear relationship. As a matter of fact, we can talk about that for every two blue circles that I go to the right, I'm going to go up 3 squares, right?
Yep.
And so every time I'm going to go to the right 2, I'm going to go up 3. I'm going to go to the right 2 and up 3. So we can actually talk about this as a rate, right? We talked about rate of change. We've actually talked about a unit rate in another video. We actually talked about taking this down to the unit rate, which would be like what, 1 to 1.5.
Mm-hmm.
Every blue circle, I would get 1.5 green squares, right? Would be my unit rate here.
Yeah, it's like a rate of change.
Yeah, so check that out. I can actually call that a line, which I just thought was a really cool thing that I thought of from the last time. And I know we're a little distracted here, but I thought of that would be a cool way to start maybe this video, since we were talking about that last time. And I wanted to get us maybe started off in this particular location. What do you think?
I love that because, you can really kind of see that line there. And honestly, that means that there's also a linear relationship. So
yeah, that
means that there's a connection between proportional relationships and linear relationships, ratios, and, linear lines. That's kind of cool. In fact, I think I have a video that talks about how you can connect those two things together.
Really?
Can I share that?
Yeah, that would be awesome. Would you share?
Okay, great. We'll go ahead and get that. Hi, everyone. It's Dr. Jones again. And today we're going to talk about how you can use graphs to show proportional relationships. Now, I've been doing a lot of talk lately about ratios and rates, and proportions are just equivalent ratios. They're just showing how two ratios can equal each other. And we can show that so very well using graphs. Now, to explain how you can do this, I'm going to bring up something that I talked about in a previous video. I'm going to bring up brownies because I love them. So in a previous video, we talked about the ratio of 20 brownies costing 50 cents each, okay? So this is a rate because we have 20 brownies and 50 cents. So it's brownies and money, different units. It's a rate, but it's a type of ratio as well, which means that we can show how graphically these are proportional to each other. Check this out. First, I need a graph.
So if we were to graph this relationship, you can see a couple of things. If we had 1 brownie, it would be 50 cents. So on this graph, number of brownies is 1, and I go up, and when I go over to the left, I'll see that it actually says the price is 50 cents. We know also that if we were to buy 10 brownies, it's $5. We found that calculation in the prior video on rates. It makes sense. It's half the price. Well, if that's the case, if I have 6 brownies, it would be $3. So look at these points. I have 1.5, 6, 3, and 10, 5. They all show the ratio relationship between the number of brownies and the price. The number of brownies here is the independent variable because the price will depend on how many brownies I actually buy. But the cool thing about this is that if I actually connect all these points together, it's forming this nice line that will help me determine other relationships between the number of brownies and the price. For example, let's say I wanted to figure out how much I can get for $4. How many brownies can I get for $4? Well, using my graph, I could go across and see, hits the $4 at the line right about there. If I go straight down, I could get 8 brownies for the $4. Maybe I want to figure out how much money it would be if I bought 5 brownies. So if I bought 5 brownies, according to this graph, it would cost me $2.50. So the graph really helps me figure out mathematical problems just using the ratio relationship, the proportional relationship between these values. So this graph is actually directly proportional, meaning that the values are very proportional to each other. And I know this because they actually go through the origin, 0, 0. So each value in this line has the same type of relationship. It's in proportion to each other. This must also have some sort of linear relationship. And I know this because there's a line. And that's what linear means. It means that they lie on the same line, the same straight line. And these points lie on the same straight line. If there is a linear relationship, that means there must be a pattern of values that I can follow to look at this relationship. So if you notice, there is a pattern. Going from each dot, each level of this line, I go up 1 and over to the right 2. Up 1 and over to the right 2. If I follow this pattern, I will actually hit every point on this line. This pattern is the slope of this line. It's the rise over the run. And in our case, the rise over the run is 1/2. Every linear relationship has a slope, has a value like this. It might not be the exact same numbers, but it has a rise over run type of value. This value is also great to show how the price is half of the amount of brownies. Think about it. If I had 6 brownies, the price was 3. If I had 10 brownies, the price was 5. The slope is showing that relationship, that it's half the price of brownies. And once again, it's going through the origin of 0, 0. So I could use this to form an equation that would signify the line, the actual linear relationship. So my X is my independent variable, that's the number of brownies, and my price is Y. Okay, so if my price is half of the number of brownies, that is shown by the equation Y equals 1/2 X, because I have to take the number of brownies, which is my X, multiply it by 1/2 to get the new price of Y. Linear relationships. It's really cool. But what if something happened? What if instead of just the price being half the amount of brownies, what if I got a deal? what if I have a deal where the amount of brownies actually I had a coupon, and I found the amount of brownies was $1 off. And with this coupon, I could apply it to our scenario. Well, how will that change my graph, knowing that I have a coupon for $1 off? If you notice, the graph shifts. It's got to shift down to deal with that discount. But in shifting, I'm still keeping the same value. I just have to make sure that I bring the price down 1. So if you notice in that ordered pair, instead of starting at 0, 0, I'm now going to start at 0, -1. And that's going to denote that price of -1 because I'm getting $1 off. The price is my Y, so it's in the Y section of my ordered pair. So the point I'm really starting this graph at is 0, -1. And that's going to be how I follow my pattern. My pattern is still up 1 over 2 because the value is still half. The price is still half the amount of brownies. That hasn't changed. The only thing that has changed is that now I'm getting $1 off of the total price. How does that change my equation? Well, I know that my slope is going to stay the same, but instead of the slope or the equation just being y equals 1/2 x, I have to account for that $1 off coupon. So it's y equals 1/2 x minus 1.
So isn't that so cool? Not only are you able to show proportional relationships through graphs, you can also show how proportional relationships are also linear, and they have a linear relationship to them as well. Hope you like this video. See you next time. Okay, so that video is just another example of how, proportional relationships, really direct proportional relationships, can also be changed and shifted so that way they relate to just linear equations. Are you listening? Hi. What are you doing?
Oh, I'm sorry. I'm sorry. I'm sorry. I got a little distracted at the end of the video there. So I was just checking out. I got some new shoes, new basketball shoes, and excited about them.
Nice.
So I got,
those are pretty good. I always wanted some shoes, some basketball shoes. Like my students love shoes. I've actually never owned a pair of like real basketball shoes. I've only had like Keds.
All right. Yeah, I got you. No.
Yeah. What size are those?
Well, so I wear an 11.5, and that's actually an 11.5 4E because my feet are kind of wide. But
okay, I have that same problem.
Yeah.
Well, okay. Let me think about this. Could I fit your shoes? I wonder if I could fit your shoes. Like our men's sizes and women's sizes, they're different, right? They're like they're to be converted.
Yeah, there's definitely a relationship between them, but I don't know if you could fit in my shoe. What size shoes do you wear?
I don't know what size shoes I wear in men's.
Okay.
But maybe we can figure that out.
I bet we can probably figure that out.
Okay, wait. So, listen. My husband just told me that my daughter, she wears a 4.5 in, women.
Okay.
And that's the same thing as a 3 in men.
Okay.
That's kind of interesting. Okay, let me share my screen. We're gonna figure this out using what we just talked about. Okay.
Okay.
So, all right. So let me just put down. We have the men's shoe sizes, women's shoe sizes. I'm putting women's shoe sizes in the independent side only because, we're talking about me and trying to figure out if I can fit your shoe. But really, we can interchange these,
Yeah, for sure.
In this situation, the men could be independent. It doesn't matter, but independent women, because we run the world. Okay, so let's just go back to what I just said. So if we put that on this graph, then what did I say? I said that it was 4.5 in women.
Yep.
And 3 in men.
Okay.
Right?
So I see that point there. Okay.
Yes. And I know that my mentee, she wears an 8.5 in women.
Okay.
And that's a 7 in men.
Okay.
Yeah. And so my cousin, she plays basketball in college, and she's really, really tall. She wears a 12 in women.
Okay.
And that's a 10.5 in men.
That's right. Yeah.
So if we were to plot all three of those points, just like we did in the other examples, we would get a nice linear line, right? So
you're exactly right.
That, right? So we have our 3 points. We have the coordinates of 3 points. So we can really figure out if I fit your shoes by using this to convert. We can use this to convert shoes.
Oh,
now,
nice.
This one isn't, you notice that it's not directly proportional because it doesn't start at 0, 0. There's a shift.
Absolutely.
There's a shift. But we've talked about that. Okay, so you said it was what, 11.5?
So I wear an 11.5, yep, in men's.
Okay, so let's figure this out. So if I were to click this, I would see this 11.5 in men's.
What does that translate to for women's?
13. Oh, it translates to 13. Oh, okay. Yeah, I don't wear a 13.
You don't wear a 13? Well, I'm sorry, you're gonna have to. You can't wear these. These are pretty awesome shoes. I mean, I would hand them over to you, but since you can't fit into them, like
I can't fit into those. I can't get it.
Okay,
I actually wear a 9.5 in women. So let me see what size in men I could actually get. So let me click this. So it looks like it's an 8. Because if you look at the 9.5, it looks like it's an 8. It's an 8 in men. So I can wear 8. Okay, so I need to go buy an 8.
Okay.
But look at that. Isn't that so
looks cool? Like, is there a relationship? It looks like we can actually come up with an equation maybe that models this whole picture. Right?
Yeah.
I think there is. Because it looks to me like, if I look at just the rate, how those are increasing, like it looks like they're increasing at a constant rate of 1 to 1, right? So like I go 1 unit to the right. If I increase 1 shoe size to the right, I'm going to go up 1 shoe size, right? As well.
Look at those 2 points. Look at point where it says 8.5, 7 and 9.5, 8. You really can see that it's the 1 to 1. You can really see
that
it
is
right
a
there.
1 to, right? So I'm able to say, okay, so I'm increasing by 1 for every 1 unit that I move to the right. But there is sort of an additive or in this case, a subtractive addition that we're doing to this too, right? We've got this little constant that we have. So just moving 1 to 1, but I've also got this constant shift down a little bit, right?
Yeah.
Like for example, if I take your 9.5 shoe size in women's, in order to compute the men's size, I can take that 9.5, but then I need to do something else to it. I'm going to subtract.
Yep.
It's like about 1.5 units, like one.
It's like 1.5 to get to the 8. So
does that work for all of them?
Like 1.5 to get to the 8.
Does that work for all of them?
Yeah, look at 13. 13, 11.5 is also a 1.5. This works out really well for this example. It doesn't happen this way for all the examples, but for this example, it works out really well. 12, same thing. 12 minus 1.5 will give us 10.5. 4.5 minus 1.5 does give us 3. There is that connection there about 1.5.
So this really is good. So what we have is an equation. We could actually write an equation. Y equals 1.5 or X minus 1.5, right? So so men's shoe size is women's shoe size minus 1.5.
It's a perfect linear relationship.
That really is. That's really great. So this was really good. Totally awesome for the ending of this video series. What a great place that we ended up on. See, we started the whole thing talking about ratios and kind of how two things vary together. Then we described about how we could compare ratios, and you came up with this great idea called unit rate. I love that. We could talk about unit rates. And in fact, we just now applied that idea of unit rate, except now we've got this idea that we can actually translate that all over the graph, right? We can add and subtract values, but we still have a linear relationship, right? We still have a constant rate buried down inside of that. Now we've just got to be able to translate it all over the screen, which is really cool.
I love it. I love it so much because it shows how everything is connected together. and it kind of makes it all one nice puzzle. And that's the best thing about math, is solving those kind of puzzles together.
Well, it's been a whole lot of fun doing these videos with you, Dr. Jones. So much fun. Thank you so much for joining me.
It has been a blast.
Yes.
Thank you so much for having me. And you really helped boost my math esteem and also just made it so much fun to see how math can be so visual and it's not always so computational.
That's awesome. Well, thanks very much, and we'll see you around, okay?
Okay, thanks, bye.
Bye.